So we finish up until here, the iterative integral, which we can switch the variable. We can choose dx dy or dy dx, and then we can switch the endpoints, and it is available, and then we can do that in double integral. So the next section, what I want to show you is before. We can start with this. The example. Okay, so first is evaluate x minus 3y squared dA, and then you have the endpoints for x and y. So basically, based on the r, we have x, right, and we have y. So we can design, okay, which one we can start with. Like for example, we can start with maybe 0, 2 here, and then 1, 2 over here, and then we can write x minus 3y squared. Then because 1, 2 is the first step, then this will be dy, and then the x. Okay. So basically, we can start with the first one here, the inside integration, which we are going to integrate with y. So you will see that we have it become xy. So let me write, we still have 0, 2. So inside is xy, and then y cubed, and then we put 1 and 2, and we still have the x right there. Okay. And maybe to make it more clear, let me write here is the y equal 1, y equal 2. Okay. And then we put everything inside, and we get this will be, so y is 2, so x 2x minus 8 minus x minus 1. So it will be x minus 7, right? So x minus 7. We need to integrate with respect to x, which we get half x squared minus 7x, and put everything inside, 0 and 2. And you will see that we have 2 minus 14, it's 12, so negative 12. And the same thing, if you want to start with dx dy, we can do that. So we can write like this, x minus 3y squared, and then dx dy. Okay, and then you can try to find. And then another typical example are evaluating the volume. Okay, volume of the solid. Okay, so volume of the solid, like this example here, number 7, example 7 here. So find the volume of solid S that is bounded by elliptic paraboloid. And you have the equation, plane x equal to and y equal to. So x equal to and y equal to, it's like the plane that is cut off the space. Okay. So we can see that the paraboloid here is basically, we can write in terms of z is 16 minus x squared minus 2y squared, and we can let this z is as function of xy, as we can also remember from the quadratic surface that we did before. Okay. So you have the paraboloid and have an ellipse on the xy, and then that paraboloid will be cut by the plane. Okay. So you can imagine, like you have like paraboloid like that, and if this is the xy, x, and this is y. Oh wait. And then you have let's say here is the 2 and this is another 2, and it's cut off the everything on this side. Okay. Also here is cut off there. Okay. So you will see that we have kind of like that, the solid. Okay, so this is our S. So which means that the volume we can write, let's just write the R first. Okay, just in a default, as a default R, and then we can write the 16 minus x squared minus 2y squared and then you can just write the A first. And then based on the plane x equal to and y equal to, we know that this will be a rectangle, right? Our rectangle. So R, we can see that R is actually a square that is in between this interval. Okay. So at the end of the day, we can take this 0, 2, 0, 2, and we can start from dx dy or dy dx. Okay. So, and then we can just write everything here, and let's just write maybe dx dy. And I believe you can solve this integration. Is any of you still maybe confusing on how to integrate like this stuff? I think it should be okay. This is just a simple example on how we can find the volume. But the idea here is to imagine like if you have like a plane or a surface, and a surface in any shape that can be defined by function of at least 2 variables, then this is the way you are going to identify, observe, and then write the process. Okay. Now let me go into more general definition, because now we still have this, right? This rectangle, which help our integration. But sometimes, maybe the area that we are going to use in the this dA, maybe the area is not a constant. Maybe it's in between a function. So we can start to think like in more general regions. Okay, so double integral in general regions. So let's consider that we have a general region like this one here. Let's say in our xy we have this D. Okay? D is, let's say, our general region, which is not a square. It's not a square. But to make our calculations similar to what we had before, let's also define our R. This is our R, and inside R is our D. And we can define the expression. For example, the surface can be determined by a function on xy when the function is inside this D. Okay? I mean, in all this interval. And then outside this D, we can define the function as 0. Okay? So this is a starter to get you into what is the approach. Okay, so we can write down that the integration, the double integration of D with respect to dA, this will be the same as with the rectangle of F dA. Okay, so as long as we can define the endpoints, then we could also compute. We can also compute. Okay? In more general, I think should give you, let me check the picture. I think you should have here, wait. Is this, yeah, this one. Okay. I forgot to mention. So basically, what does it mean is we want to compute this. Then this is not a square, right? We want to compute this with the help of the square here. So then, after we see this connection, we see also if we can define this d in terms of function, either function of y or function of x, either way. For example, the first case here is in the function of x. So if the d can be determined by like a two function here. So this is the function one, g1, g2, and let's say this is g1 over there, and g2 is here, and another one is g2 is here, and g1 is here. So as long as we can define this g1 and g2, then we can also define this g inside our endpoints. So that is actually our goal. So as d is on the two variable xy, and let's make the x as our constant and y is function of x, which means that we have g1 as the bottom equation and g2 in the top. Okay, so we define first, this is our d. So we are expecting that we are going to take this y in terms of function of x. And because it's a function of x, and this is a constant, to write in the double integration, okay, by intuition. Okay, so we are not yet going to detail on how we are supposed to do, but by intuition, because this is a function of x, and then at the end we are expecting a constant x, then this function of x needs to be computed first. So when this happens, it means that we are going to compute dy and then dx. So this will be dy dx, okay? Because the constant is x. Okay? So okay, let me write in the new page here, okay, to give you more clear idea. Okay, so let's say this is our approach. Okay? We have a square and we have the d. So as we mentioned before, so d is fxy dA, and then this equal to r, and then this is capital F, and then the a, and this capital F is equal a c b d f x y dA. But that is on the square, but we only need the d. So we write that f x y is 0 if y is less than g1, and then or y is greater than g2, which means outside the d we can set that it will be 0. So it means that we can perform the double integration. Then as a conclusion, then the integration of CD on the fxy dy, this will be equal to the g1x to g2x of fxy dy, and this will equal to the small f, so we know that from our previous assumption that this capital F is equal to small f when y is in between this g. Okay, so it's okay if you're not really understand what is really happening here. So actually, we are kind of developing the definition from the first double integral that we got, which includes the square, the rectangle, right? But now we want to make the regions as just a normal regions, like it can be any curve, it can be any shape. But we want to make sure that we can make the double integration. So we can set up some definition that we can set a square, and then we can double integrate. But when we are in the blue area, we set that it will be equal to 0 because we only care on the d. So we can just say that this dy for CD, like this one here, CD, for this one we can equaling to this new function of f, and it's actually equal to this small f that is going to evaluate from G1 to G2. Okay, so that is how it goes for definition. But it's not, if you're still like not really convincing, like what's happening. Well, we can just visualize through the picture, and then let's just using our intuition. Okay, so if we have something that is in the xy plane, for example, and then you can define each one of them as a function of the other one. It can be function of y, function of x. It means that if we put into double integral, that functions that is the endpoint will be our first step. Will be inside integration, and the outside integration will be the constant. Okay? So your textbook, like defining this and makes the name. This one is type 1, the other one type 2. Personally, for me, not important. Type 1, type 2, no need to like really emphasize, oh, we need to know the type 1, type 2. No. You can think like freely, as long as you know which one is the function. Because sometimes the function can be switched. You can switch, like you want to, for example, y equals something something x, but you can rewrite x equals something something y. Sometimes there are functions that we can switch easily. That means we can choose dy dx or dx dy, up to us. And sometimes maybe the other one maybe looks easier, and maybe the other one maybe not really easy to solve. So I think that is one way to solve. Like if we think clearly which function that is suitable, then maybe we can switch the type, switch the function. But let me just go through this definition. So by taking this, okay, as I mentioned, then we can start from dy first, and later after we get some result inside, then we integrate one more time with a constant. Okay. So I think by this order, you can see that it's actually quite reasonable that the result will be like we are going to get a better result. Right? We are going to get there. Okay. So the only thing that is, I think, important in these regions is actually the functions in the like which one we need to compute first, like dy dx or dx dy. That is the important thing. So understanding the functions, how they look like, which one is on the top, which one on the bottom, that will be important. So identification will be important here. So we write here. So we need to identify clearly the function g1 of x and g2 of x. Okay, if we can identify which one is on the top, which one on the bottom, then we can just put in and then just compute. And usually the computations, like the calculation inside here, somehow not really that complicated. Usually not complicated. It will be like straightforward. You can just compute as usual. I think the difficult part is to set up this double integral. Set up which one is the functions. Okay. 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 I think before example, I think we can look for the other type that is mentioned here, which your textbook described as a type 2. And let's say I don't really care like which type, as long as we know what function we are dealing with. Okay, as long as we know, then we should be okay. We should be fine. Like here, we clearly see that x is equal function of y, okay, which means that we are going to see that expect the top will be the right. Okay. Remember, in calculus 1, we also see this the integration, right? The area between curves in calculus 1, if you remember. Like how to get this reason or logic. We can think like, we can see like which one is like, you see top and bottom. The top is here and the bottom is here. If you see from this side, right? If you rotate your hand and okay, this one is on the top. Okay. Sometimes you forget that okay, you can rotate this the curve. You rotate this the curve. Okay, this is on the top. Okay, if you don't remember. Okay, so that means this H2 is come on the top here, and H1 is here, and this will be dx dy. Okay. Okay, and this is we call it type 2. But for progress, like how to solve, you don't really need much care on which type, like 1 or 2. Doesn't matter as long as you know how to identify the functions, right? Okay, I think we can go to example. Okay, example. So I give you this example 1 here with the picture already here. So evaluate, and we are given the double integral, the function, the surface. So this means that this is the surface, and D will be the region that is on the area. Okay. So the region is between the parabola, two parabola, and we have the picture here. Sometimes the picture are not given, so you need to use your any method of drawing the curve, sketch the curve. Okay. I think 2x squared easy to imagine. Like this is just a normal use regular x squared, but you multiply by 2. So it means that you will have the scale is a little bit different. And then the other one is 1 plus x squared, which is x squared, but you move 1 unit up. Okay, so that's why it's going here. And another thing, so it's pretty similar to what we have in calculus 1, especially the area between curves. So the important thing in calculus 1, when you deal with this kind of area, is finding the intersection here. Because if we are just given this question, then then we need to know like how do we integrate if we don't know the interval, right? So we need to know the interval. To know the interval, we need to find this intersection. So let me write here. So first is we are going to find the intersection. Okay. So to find the intersection, we are going to equaling the functions. So we have y equal to x squared, and another one is y equal 1 plus x squared. So we are going to equaling these two and solving that this will be plus minus 1 for x. So when x equal 1, y equal 2, and for x equal negative 1, y is also 2, right? That's how we get this point. Equaling these two boundary and then get the intersection. And after that, we can start to take. So now is the computation for the which method we prefer. Do we prefer dx dy or dy dx? As we can see, that we can clearly see that this two is like the first one is on the top and then this is on the bottom. So I think we can deal with the dx as a constant. So we can draw the rectangle like in your area integration. So this is the x like that. It means that we are going to take the double integration. Let me just write the question first. So by taking the rectangle dx, it means that the constant will be x. Okay, the constant will be x. So x will be start from -1 to 1, and then the inside integration will be from 2x squared to 1 plus x squared. Okay. And then we take this, and then this is dy dx. So we start from dy first. So dy, we are going to have xy plus y squared, right? And this will be input this two equation, which we are going to have a little bit long equation, but I think still okay. So we are going to compute and still in the integration, -1 to 1, and write everything. 1 plus x squared plus 1 plus x squared squared, and then minus 2x, or maybe x and then 2x squared to make it more clear, and then minus the 2x squared and then squared, and then all we are going to integrate with respect to dx. So we need to expand first. So let me, so we expand all the terms. So this will be x. Let me write here x plus x cubed plus 1 plus 2x squared plus x with power of 4 plus minus 2x cubed minus 4x with power of 4. And then we combine everything. So we have -3x with power of 4 minus x cubed plus 2x squared plus x plus 1. And then this is the x, and we integrate one more time. Okay. So we get -3x with power of 5 over 5 minus 1 over 4x with the power of 4 plus 2 over 3 x cubed plus x squared over 2 plus x, and then plug in -1 to 1. Now when this happens, and in our class. You can use your calculator in the exam, so I think still okay. So you plug in, and end result is 32 over 15. Okay, perhaps one more example, but I think maybe we are not completely solved. Maybe tomorrow we are going to continue. So let me just write the question. So let me write find volume of solid under paraboloid z equal x squared plus y squared, and above region D in xy plane, bounded by y equal to x and y equal x squared. So you have a line equation and also the parabola. So the step is draw region, okay, draw region, and then identify the function. Set the double integral. Sometime maybe you need to reverse order if needed. Okay. So sometime if needed, you can reverse, like making dx dy to dy dx. And there will be some cases that you need to take care of the reverse order carefully when we deal with the functions. It's not the same when we did in a constant. If you remember, if we have a all constant, we can reverse the order easily. Okay. You can just practically reverse. But when we deal with the functions, it means that we are going to define another function in another variable. Right? So it doesn't mean it's as easy as reverse the order like regularly. So we need to imagine and visualize how the function will be, because function will be changed. Okay, later we are going to discuss about that. Okay? But I think I will end up until here. Okay, we are going to discuss this tomorrow and with other example. Okay. Any question first? Sometimes, if you see the integration and then you try to integrate, and maybe it's not easy to deal with. Maybe you need to reverse. Yeah. Yeah. Basically, yes. And especially for the one that has like a function in the endpoints, there will be a question that you need to reverse. If not, then it will be impossible to solve. I think that will be for later discussion. Okay.